I think we're about ready to get started. Well, hello everyone, and welcome to the first phase of the Computer History Museum this evening. And I want to welcome everyone on behalf of the trustees, the staff, and all of our members, because we have a special event this evening, as you know, and it's been sponsored by Sun Microsystems, the Mars Exploration Rover Project, something that I think is pretty exciting in a lot of different ways. I'm John Toole, the Executive Director and CEO of the Computer History Museum, and this evening's event really focuses on a lot of, and perhaps the most important expeditions in space. Many people actually rank this as the most outstanding achievements of our lifetime. Its really significance ranks up there with, someone landing on the moon, which happened on July 22nd, 1969. Both of these journeys required breakthrough advancements in computing technology all across the board. Peter tonight will probably tell you a lot more about it as relates to the Mars expedition and show you how engineers really push themselves beyond their limits to make it real and to translate those inspired imaginations into something real and concrete that we all saw and really have loved. We take for granted really the vast amounts of computing technology that performed essential mission planning calculations on the ground before, during, and after. And I think you'll hear some of that and how important that turned out to be for the trip. It's really an extraordinary technological advances such as these that forever influence the technology base that we touch every day, that truly impact us in the way we work, live, and play. And this is what the Computer History Museum really is all about. I'm also happy this evening to make an announcement. Starting in September, the museum will bring to you our newest program. It's called Odysseys in Technology. It's a series of events sponsored exclusively by our friends at Sun Microsystems Laboratories. The Odysseys in Technology series presents people and perspectives behind the world's most extraordinary innovations in computing history. It's yet another way the museum lives its vision of exploring the computing revolution and its impact on the human experience. Within the next few months, you'll be hearing about programs focusing on a wide range of history-making advances, from computers and their roles in graphics and music to public key cryptography and computing and trends in industrial design. I think you'll really enjoy this. I want to invite all of you to come back and learn more about some of the most important stories of the information age. And again, thanks to Sun and all the dedication and help to really making this happen, this landmark series for the Computer History Museum and Sun as a partner. Thank you. Meanwhile, I want to tell you about one other program we're starting up kind of on a test case, and you're invited to come back really tomorrow evening. The museum is opening its first of 3 summer movies in the Computers and Film Cinema Series. Now, this is a cinema series where computers take center stage in the movie itself. Okay, this is sort of a fun thing. Tomorrow's movie, of course, is The Computer Wore Tennis Shoes with Kurt Russell, Cesar Romero. So gather your family, your friends, and get here tomorrow by 7 o'clock. Enjoy popcorn, peanuts, whatever, and we'll have some fun. And be sure to wear your tennis shoes. There'll be 2 other movies that'll be shown in August and September, so please check our website for details. And for a little longer term, October 19th, save the state and join us for the Fellows Awards. It's really a spectacular event that will be held in this room in a different configuration, and we'll celebrate 5 computing heroes and their personal stories. So if you haven't heard about us or know about us, and I know many of you are here maybe for the first time, pick up some literature. I hope you've been reading some of these screens before I got up and talked, but talk to one of us and our staff. We'd be glad to fill you in. There's a lot of exciting things happening, and this is only our first phase, because we're eventually going to build out this whole building into a world-class museum and a community experience for everybody to enjoy, something that's really important. And each and every one of you really can help build this great institution, from members, major donors, donors of artifacts, volunteers, and collaborators, and really proud of that. But really for tonight, let's get ready for a talk that'll take us from terra firma to the red planet. And to tell you more about this, I want to take a moment to introduce to you Glenn Edens, the Vice President and Director of Sun Microsystems Laboratories. Glenn, who is probably one of the premier thinkers of our time, or at least that's what he told me. Actually, I got this from somebody else. Has really an extensive background as a researcher, entrepreneur, corporate strategist, and consultant in telecommunications, entertainment, and computer technology design. At Sun, he manages research and development at all three Sun labs in Mountain View, Burlington, and Grenoble, France. Prior to joining Sun, he was president of AT&T Strategic Ventures and also served as VP of Broadband Technology for AT&T Labs. And from 92 to 98, Glenn was at Interval Research Corporation in Palo Alto, managing research and the transfer of research results into external product companies. So Glenn knows an awful lot about these kind of things. And in 1985, Glenn founded Waveframe Corporation, which developed the first all-digital audio workstation for the motion picture, television, and recording industries worldwide. Glenn and his company received an Oscar from the Academy of Motion Picture Arts and Sciences for its pioneering work in digital audio. And of course, you know, Glenn, we're really proud because you may be the only person that we've ever had on this stage which was an Oscar winner. And on top of this, in 1979, Glenn co-founded another corporation called Grid, which really was a company that developed one of the first laptop computers ever. He has served on several boards of directors for nonprofits and public corporations. Please welcome Glenn Edens. And again, Glenn, thanks for all your help.
Well, thanks, John. I didn't expect that because the real introduction tonight is for Peter Theisinger. The talk we have tonight is really exciting. Peter has come from JPL NASA to tell us about the Spirit and Opportunity Rover Project. Here up on stage we have Rocky 7, which is one of the prototypes that was developed originally for the Pathfinder mission. And some of you are here today with the Sun Labs event. We've been taking over the Computer History Museum this week, and we've had the pleasure of actually playing with Rocky a little bit today, so that's been a blast. But let me talk about Peter. Peter's been with NASA JPL since 1967. And he received his Bachelor of Science degree from Caltech in physics in 1967. And he's currently the manager of the Mars Science Laboratory Project. Peter's had a really wide range of exciting projects and assignments at JPL. And one of them here I really want to ask him about later. He was the deputy manager of the Mars Sample Return Project. I don't know how many of you have ever been asked to return a sample. But be fun to find out a little bit more about that. And during that career at JPL, he's also been Deputy Manager of the Systems Division, Mission Support and Development Manager for the Mars Surveyor Operations Project, and a number of other really exciting projects at the labs. So I'd like to introduce Peter. And where is he? There he is.
Can you hear me? That was not a commercial. I always start these talks by a little feedback. By claiming that when this project started I was really 25 years old, and that the gray hair is all a result of this project. But given the resumes that I just got read, that's probably not going to convince anybody. I'm going to tell you a story. I'm a storyteller. The people that work with me know that. And so I'm just going to kind of walk through the chronology of how we got to where we are today on the Mars Exploration Rover Project. As Glenn said, I was the project manager of that project from the beginning until about 2 weeks after Opportunity left the lander. And then I went and took another assignment. And no good deed goes unpunished. So I get to do it again in 2009. This is where we're going, or where we are. It's a picture of Mars. Mars has approximately the same land area as Earth, although it is significantly smaller, and the surface gravity field on Mars is about a third of what it would be on Earth. So you'd weigh about a third of your weight. It's a very dry planet. If you took all the water in the Martian atmosphere and had it precipitate out on the ground, it would cover the ground to a thickness of a little bit less than a paper, a slice of letter paper. The temperature extremes are marked. easily at the equator where the rovers are close to. Plus and minus 100 degrees centigrade per day are kind of routine, probably a little bit more than that in the wintertime, which is kind of where we are right now. What you're looking at right now is the side of Mars, which has Valley Marineris here and the Tharsis Bulge with Olympus Mons over on this side. And so Spirit is really right up here. Opportunity is right up here, and Spirit happens to be on the other side of the planet. Glenn mentioned the Mars Sample Return Project, one of my, I don't usually include that in my resume. The Mars, if you recall, we visited in Viking in the 70s, and the purpose of Viking was to determine whether or not there was life on Mars at the surface. And that mission did not find life, and as a result of that, for about 20 years, no other spacecraft went to Mars. In 1996, 2 spacecraft went to Mars. Mars Global Surveyor, which went into orbit and is still sending pictures back, and Pathfinder. The goal of Pathfinder was to show that you could land on Mars with a novel technology, airbags, and that you could do so for a lot less money than Viking spent. Viking in today's dollars would be about a $3.5 billion project, and nobody wants to think about that in today's budget climate. And so Pathfinder attempted to do it and did for a little bit under $400 million, everything included. Mars Global Surveyor found, in taking pictures from orbit at much greater resolution than Viking ever did, that although Mars was dry and had no surface water now, there were clear signs that it had had a wet past. There were things that looked unmistakably like river deltas, river basins, teardrop shapes, flow fields in rivers, those kinds of things. And so the question became, did Mars have a wet past? If it did, how long did it last? And if it lasted long enough, is it possible that a habitat suitable for life could have been there, and could life have started? On Earth, we know that life is pervasive. Even in stressful habitats at the bottoms of oceans and sulfur springs and those kinds of things, we get life. And so the question of where has the water been, where has it gone, how long was it there, became NASA's mantra. And things were going fine until September of 1999 through January of 2000, when the 1998 missions, a orbiter called Mars Climatological Orbiter and a lander called Mars Polar Lander, went to Mars, and both failed. The orbiter failed because of a navigational error, the famous English versus metric units that you probably have heard about. There's more to that story, but catch me later. And the upshot was that the orbiter got too close to the planet when it attempted to go into orbit, and actually entered the atmosphere at the velocity it was going, it burned up. The lander, of course, that accident happened in September, and the lander was due to arrive in December, and everybody took that failure to heart, and they, as one of my managers said, they not only turned over every stone, they raked the gravel. And still there was a software bug, presumptive failure mode, a software bug, in the lander that caused the retro rockets to cease firing about 40 meters above the surface, and it could not tolerate that kind of a fall, and it also failed. And so at that point, the ongoing Mars program stopped. And the ongoing Mars program at that point in time was a 2001 orbiter and lander in development, boxes built, ready to enter integration and test at Lockheed Martin in Denver, Colorado, and on the books, the 2003-2005 Mars Sample Return mission with me as its deputy manager. And it was clear from the 98 accidents that NASA's ambition was too high. The world of better, faster, cheaper was probably causing problems because of resource restrictions, and that we were just being too aggressive with the program, and we need to have to recenter our thinking and reconstitute the program as a result of those failures. However, Mars opportunities come around every 26 months. That's when the planets get into the right alignment to go to Mars. And as you all know from the press you saw last summer, the 2003 mission to Mars, opportunity to Mars, was a cherry chance to go. It was the best geometrical opportunity for 2 decades. It was a little bit closer. That's why the 60,000 year quote gets quote. It was closest it's been in 60,000 years. These things go in cycles of about 18 and a half years, and this was just a wonderful opportunity. Now, for people like me, what that means is that you can get a given mass to Mars for a smaller launch vehicle, that the time to get to Mars is less, so when you are at Mars, arrive, you're close to Earth, communication rates are high. Turns out in 2003, you're also close to when Mars is closest to the Sun, so for solar-powered rovers, it's good. What's the V infinity, what we call the V infinity, which is the velocity at which the vehicle hits the Mars atmosphere, is low, which means your thermal protection system has a lot of margin. And the landing ellipse, these things are ballistic. You throw them into the atmosphere, they land where they want to land. And so navigation errors at the top of the atmosphere give you a dispersion on the ground. And for the 2003 opportunity, those ellipses were very small. We'll talk about that a little bit later. But Pathfinder's landing ellipse was over 300 kilometers long, and the MER landing ellipse, depending upon which site you look at, was somewhere between 70 and 90 kilometers, which meant there was a lot of places you could go now that you couldn't go before. So NASA began an investigation to find out what are we going to fly in 2003 because we don't want to not go. But in 2000, in the summer when they were making these decisions, in the early spring, we had much less than 4 years to do this. And in my business, it takes 4 to 4.5 years to put a spacecraft, interplanetary spacecraft together and test it and get it done. So the key issue was, what can we beg, borrow, and steal that we don't need to invent? And if we inherit a good enough system, we'll take it. In that context, they had a big review. Isn't that what you always do, have big reviews? And a lot of people came. And a small group of people, who we have not yet forgiven, came. And they presented something called Mars Mobile Pathfinder 2003. It wasn't even on the radar screen 6 weeks before this meeting. But it came out one of the 2 finalists. And it said, well, we know how to land on Mars. We did it with Pathfinder. So let's use the entry, descent, and landing system from Pathfinder. That means the parachute, the retro rockets, and the airbags to land safely on Mars. I'll show you some pictures, but from the tetrahedron structure, which is the thing that the rovers were in and the Pathfinder electronics were in, from that all out, we'll just build the print. We'll just take all the old drawings and we'll just make it. Airbags, everything. Sounds great, right? Inside, where the electronics go, we'll just add wheels. Well, that's a little simplification. There was some rover design work that had gone on at JPL. There were a couple of discovery projects and some other proposal efforts, and so they borrowed on that. Rocky 7 here is an example of that was used to help develop roving technology. Sojourner came out of that, but the technology program kept going with more ambition and larger products. And we had a payload, because the 2001 lander suddenly wasn't going to go to Mars. NASA wasn't going to let that happen. And so we had a set of science instruments just sitting in Denver. So that was the plan. Let's take Pathfinder, let's take the rover technology, let's take the payload, we'll put it together. In 37 months, we'll launch it to Mars. I mean, after all, what could go wrong? The next hour, we'll talk about the answer to that question. Okay. Here's a picture that they showed. This is actually from their presentation. This is the cruise vehicle that goes to Mars. This part here is the entry vehicle. We'll see a little bit more of that later. All this stuff is the stuff that you need to get to Mars, but you don't need to land on Mars. Fuel tanks, star tracker, those kinds of things. Here's the tetrahedron, and you see how this rover is all kind of folded up here. This mast is laying down, this antenna is folded up, the wheels have to kind of scrunch up underneath, toe in, all to fit inside this tetrahedron. So this was the plan. Okay. As a result of the meeting, NASA said, well, we're going to start 2 efforts. One, what became the Mars Exploration Rover Project, and the second, a 2003 orbiter. Kind of go on parallel tracks for about a month or 2, and we'll see who wins. There was a shootout in July. The advantages of the lander I've talked about. The advantages of the orbiter are similar, but not quite as persuasive. But the thing that really swung the decision was we had instruments and they did not. And it was felt that in order to really make a step forward in the 2003 mission from Mars Global Surveyor that was there and Mars Odyssey, the 2001 orbiter that would soon be there, they really had to do better cameras and better spectrometers. And those of you that get on the websites and look at the Mars Express photographs and spectrometer data can really see what good instruments will really show you. And it was felt that rather than going in 2003 with the orbiter, that they would go in 2003 with the lander, and the orbiter would wait till 2005. And in fact, the orbiter is being built as we speak for a launch next year. So in July, NASA selected the MER project, and after Ed Weiler, who was the Associate Administrator for Space Science, made that decision, he took it up to Dan Golden, the Administrator of NASA at the time, and said, "This is what we're going to do, Dan." And Dan said, "Why not fly two?" At this point, we only had one. So I received a phone call to give a cost estimate for the second rover, due in 45 minutes. You probably understand how accurate that cost number was based on that piece of data. And they bought that. Golden went around and held out the hat to all the other codes in NASA and collected, I think it was around $250 million from them, and they ponied up a second rover. In August, after we had kind of convinced them that we thought we knew how to do that, they selected the dual mission design, and the project entered the preliminary design phase. So by August, we'd got the concept, we knew what we were doing, we were going to go. At this point, in May, the 5th of May was a Friday, 12 noon, my boss came up to me and said, "How would you like to run this project? This guy's your deputy, here's your flight system manager, and here's his deputy, your staff is now 4. And I said, "Why not?" By Christmas time, we were up over 270 and screaming. Okay. Also by Christmas time, we were broke. Okay? The build-to-print heritage of the Pathfinder entry descent landing system was lost, was gone. Okay? The rover would not fit inside the tetrahedron. We didn't have enough mass margin and volume margin, and we had to create something, so we had to make the tetrahedron bigger. Now, the tetrahedron had to fit inside that entry capsule, which had to fit inside the launch vehicle shroud, so bigger did not mean a lot. If you put on this stage the two tetrahedrons, you would not be able to tell the difference. They are 2 inches difference in size. But that made all the difference to us in terms of volume. It also made all the difference in terms of all those design drawings that were now so much waste paper and had to be redone. Okay. In addition, the mass growth meant the parachutes had to get better. The retro rockets had to get bigger. And the airbags had to become more capable because they were going to land a heavier mass on Mars. Okay. So this idea that we were going to start with a heritage project so that we could build it in 37 months disappeared in about 6. And we had 30 months to get it all done again. And, of course, a little bit more money. In January of 2001, we had another piece of news. There were some residual Pathfinder airbags sitting around, and we took them on a drop test. You'll see a picture of what that facility looks like a little bit later, but there's a very large vacuum chamber at Plumbrook in Sandusky, Ohio. It's about 60 feet high. That's used for testing launch vehicle shrouds and other large things. And that's what Pathfinder and MER used to do airbag testing. You cannot test the airbags in 1 atmosphere because the atmospheric drag is so high you can't get them going fast enough. And so you pull them down on bungee cords, a very scientific method. You pull them down on bungee cords from the ceiling of this vacuum chamber onto this inclined ramp full of rocks, strategically placed to break them. You measure the velocity with a radar gun, you take high-speed photography, and you see what kind of damage you cause. So we did that in January of 2001 to kind of verify our heritage. And they failed. Now, these airbags had not been stored correctly. The airbag material is sensitive to ultraviolet light and degrades in that kind of an environment. These airbags had not been stored in controlled conditions. So the project believed the existing analysis and accepted the explanation that the root cause was storage damage to the airbags. You'll notice the last sentence here. Okay? That turned out to be wrong. But we didn't know that for another 9 months. But by mid-2001, the baseline design was in fact completed. This is the rover. It stands at its eyes here about 1.7 meters. It's right about my shoulder level. It weighs just under 180 kilograms, just under 400 pounds. The wheel track here is, I think, about 1.5 meters. The wheels are 25 centimeters tall, which is also about the height of the oil pan here. That's what I call it. I kind of walk around it for you. This is the PanCam mast assembly. Stands for panoramic camera. Up here, there are 4 cameras, 2 stereo pairs. One stereo pair is the science cameras, very high resolution, a very small field of view, a lot of filters on a filter wheel to dig the science data. The other set of cameras are navigation cameras. When the planners planned the rover drive, they don't need really good photography. And so in order to keep the bandwidth down, in order to keep the data return down, they take lower resolution, wider field of view pictures. And so those cameras are 45-degree fields of view, much lower resolutions. This tube also serves as a periscope for a thermal emission spectrometer that sits down here where it's warm. And there's 2 folding mirrors at the top that pass the light down. So this tube also happens to be the foreoptics for a far infrared thermal emission spectrometer. Also up here on the deck are the solar rays. You can see the solar rays. You'll notice that the solar rays fold up. They have a little hinge here, so there's a first part of the solar ray and a second part of the solar ray. That was because we discovered, as part of the early design effort, that we did not have quite enough solar ray for the power requirements of the rover, so we made them a little bit bigger and put this extra complexity in there. This is what's called the lollipop antenna, X-band communication, direct to Earth, both send and receive. This little pencil back here has been the big surprise of the mission. At Mars, on Mars Global Surveyor, there is a UHF frequency receiver. And on Odyssey, there is also a UHF frequency receiver. And we actually relay data at UHF to those orbiting assets. They fly overhead twice a day. Mars Global Surveyor about 2 o'clock in the afternoon and 2 o'clock in the morning. Odyssey about 4:30 in the afternoon and 4:30 in the morning. Their horizon to horizon can vary from as little as 3 minutes to 12 minutes. And we have gotten, to date, 92% of the data via that link. The original plan was that we would get 50% here and 50% here, and it turned out that the UHF has been a big and pleasant surprise for us. This is the low-gain antenna. Down below here, you see the 6-wheel, what's called the rocker bogie system, very much like the Rocky 7 rocker bogie system, you see, with a bunch of linkages to help it unfold. In front, there is the ARM, instrument deployment device. It's a 5-degree of freedom arm. It's got a shoulder joint, just like your shoulder, and an elbow joint, and a wrist joint, and then a turntable at the end to bring the various instruments into play. It's about the length of your arm, as it turns out. In fact, Steve Squires, the principal investigator, will tell you it's exactly the length of his arm. That was a design requirement. There are 2 spectrometers, a Mossbauer spectrometer, which is really good for looking at ion minerals, and a alpha particle X-ray spectrometer, which is really good for looking at elements. The microscopic imager, which you've seen, I'm sure, pictures of, which is like a little geologist's hand lens that you can see really fine resolution photography of. And the rock abrasion tool, which is a little like orbital sander that allows you to drill below the weathering rind that's on the outside of the rocks and see the crystalline structure that's inside. This is a poignant story because it was built by Honeybee Robotics. And Honeybee Robotics is on Manhattan Island, just a handful of blocks from the World Trade Center. And they were there that day working and testing when September 11th happened. This is how it all goes together. This is the rover. It folds up into this little tetrahedron. I still don't believe that it fits, but it does. You'll see pictures later about why I don't believe. The tetrahedron folds up, and the airbags would go on the outside, and sits inside the back shell and the heat shield. The cruise stage sits on top. It's got solar panels for power on the way to Mars, propulsion tanks, as I mentioned before, electronics you don't need once you get to Mars. The entire thing weighs a little over 1,100 kilograms, and it's extremely dense. It's about 1.5 meters high and about 1.7 meters or 8 meters high by about 1.8 meters across. So extremely dense packaging. I'm going to show a video now which is going to describe the most perilous part of this whole process of getting to Mars, which is the entry, descent, and landing. So, Mike, can you show me the video? The people here are actual engineers that were intimately involved in the entry, descent, and landing activities and design.
EDL, that stands for entry, descent, and landing. But its main job is to take a vehicle that is streaking across interplanetary space. These speeds that our spacecraft travel are just tremendous, and get those speeds down to practically zero on the surface of Mars. We have a heat shield, we have a parachute, we have rockets and an airbag. And we have to use all those elements and very quickly and get it all done in 6 terrifying minutes.
Everything we do in EDL is decided by the computer. We have different sensors that trigger different things, and there isn't time to call back and say, hey, the winds are higher than we expected, or you know what, I'm going to hit a big pointy rock that's going to hurt these airbags. It's all about autonomy. I think that's probably, in my mind, the most challenging part. It's just lack of control.
The spacecraft hits the atmosphere of Mars at 12,000 miles an hour. That's time zero for our entry, descent, and landing sequence.
When we hit the top of the Martian atmosphere, we're moving at a speed of 25 times the speed of sound. That's like 20 times faster than a speeding bullet.
And that atmosphere is thick enough that it's going to turn the front end of that heat shield about as hot as the surface of the sun.
Hot gases have enveloped the spacecraft, and the outside skin of the heat shield will reach a temperature of 1,600 degrees Celsius. This lasts for 30 seconds.
There's a huge temperature difference from the inside to the outside of the heat shield. The vehicle on the outside is getting thousands of degrees centigrade, while the inside may get up to barely room temperature.
We go through what's called the heat and deceleration pulses. As it slows down through the supersonic speeds and approaches Mach 2, we open a parachute. We're going now about 1,000 miles an hour.
So that parachute comes out, it really slows the vehicle down really fast, and it brings us from going almost sideways to bringing the whole vehicle almost vertical.
The Mars surface is rapidly approaching. We're still moving now about 250 miles an hour.
20 seconds after we deploy the parachute, the spacecraft is slowed to subsonic. In other words, at this time it's moving slower than the speed of sound. At that point in time, we jettison the heat shield.
And then 15 seconds after that, the lander pops out and repels down a 20-meter-long bridle, a rope.
So what happens is while the lander is being lowered from the back shell, the whole spacecraft is hanging on this cord here. And it's really about the size of a shoelace. It's not much thicker than that. So when that's done, we've got this really neat system. We've got the parachute on top, the back shell in the middle with the retro rockets, and the lander down below.
At this point in time, the radar will have acquired the surface. It'll be in lock with the surface.
And once it sees the ground with the radar, it figures out how fast it's going and how high it is. From that, it can do the math to figure out how long the rockets need to be on.
We added very late in the project a descent imager. It's a camera that takes 3 pictures and compares high contrast items in those pictures to try to determine the horizontal velocity at which we're moving across the surface to help decide which transverse rockets we're going to fire.
At this point in time, we have to fire the retro rockets, or we're going to slam right into the ground.
And just about 5 seconds before we hit the surface of Mars, we inflate the airbags in the lander, then we light the retro rockets. The retro rockets bring the whole system from about 150 miles an hour down to zero, about 15, 20 meters off the surface.
And then we cut the bridle. and the airbag falls the final distance to the surface.
Net velocity when we land is about 24 meters per second when we hit the surface. We hit hard, we bounce high.
Smack! The first impact, 40 Gs. We bounce just as high as we fell from, and then smack again, nearly 40 Gs.
It could kill it right there. The first bounce, if the rocks are in the right formation, if you hit the bags in the right way, our system isn't bulletproof. It has Achilles heels, and if the rocks want to find those, they can.
And then bam, again and again and again, some 15 to 30 impacts, each slightly smaller than the previous one, until finally we end our last minute in this rolling, bouncing rollout that terminates with the lander sitting quiet at 0 miles an hour on the surface of Mars. And that's it. MER has landed. EDL is complete.
You could tell the passion they felt, can't you? You know, I think we'll talk a little bit later, but one of the reasons this thing worked was because of that degree of commitment and that degree of concern and that degree of fear, frankly. I'm sorry? I don't know an answer to that question, but if you check the JPL website, they put an awful lot of these videos on for downloadable content. And if you can't do that, then the path to Pete's email goes through the History Museum, and you can email me and I'll find out if it's publicly available. Certainly should be. There's another one later you're also going to want. Also in 2001, we started the landing site selection process. And as I said, because the landing ellipse was so much smaller on MER than it was on Mars Pathfinder, there were a great number of landing sites available to us. The Beagle landing ellipse was so large that Beagle could only really go to one place, and that was Isidis. You'll see a map later. Pathfinder really had a selection of about 6 landing sites, and they chose to go very close to, in fact, where Opportunity ended up landing. Opportunity had 100, and Spirit had 180 landing sites identified initially. And in fact, the challenge was to get that number down very quickly, because all those landing sites had to be certified. We had to make sure it was safe enough to land there, and that meant taking orbital photography in stereo to be able to see how much craters and rocks there would be, measuring the ground reflectivity for radar, measuring the albedo for temperature, and because at the time we only had Mars Global Surveyor as an orbital asset, we needed, a little bit later we got Odyssey, we needed to get the numbers down quick so we could focus down the photography on just the places that the scientists really wanted to go. We got to October, and we had brand new airbags, and they failed. And that forced a re-examination of the airbag design and a significant extension of the schedule for additional fabrication and testing. We dropped 50 airbags on this project, and in fact, we did some drop tests after launch in order to confirm that we, in fact, were going to the right places. I'm going to show you a few photographs here. This is the picture looking up at the airbags coming down. You can see this ramp is tilted 60 degrees up, so you're really looking almost straight up here. And you can see how the rocks are placed strategically to cause maximal damage to the engineers. Not shown in this one, because I think this is actually a Pathfinder photograph. We had what we called the black rock, which we always felt that large rocks were dangerous. Small rocks weren't dangerous. And then we dropped a test on, and the black rock, which was not very big, got us. And it became kind of the evil rock for the project. The question was, did we survive the black rock? Kind of was the question. One of these rocks on MER was in fact a plastic bubble, which we had sprinkled with little sharp things on the outside, but we put a camera in the bubble. And so this is what you see if you're inside the rock and the airbag is coming by. The airbag is moving from your left to right. This looks pretty bad. This is great. Okay? The airbags consist of a layer of fabric and originally 6 layers of thin, what are called abrasion layers. The abrasion layers are sacrificial. They are meant to rip, tear, dissipate energy, go away. Eventually, when we fixed the airbags, we put 2 bladders, 2 inner layers on, one to hold the pressure, one to provide structural support, and 8 abrasion layers on. And that's what the configuration that we actually flew to Mars. So here this rock's coming in, and it's ripping here. That's okay. Time continues, and more damage is being done. Okay. And very hard to see in this print, but right here, right there, that thing that looks a little dark there, that's a hole. Okay, that's not good. And it was caused not by the ripping and tearing of the sharp edges of the rock, but by the compression of the hit. Okay, it's like, I don't know if you ever had the experience of slamming a tire into a curb and getting a flat and looking at it and not being able to tell why it failed, but it's a compression failure. You hit it so hard and the thing's just structurally failures and it rips. And so this is that caused us to go back to the drawing board. And as I said, the solution was that we, rather than having a single interior bladder do both jobs of holding the pressure, which is only 1 psi, and providing structural strength, we separated those 2 functions. We put an inner tube in our tire to hold the air pressure. It cost us 10 kilograms, which we didn't really like, but it was what we had to do. In addition, we had parachute strength test failures in May of 2002 that forced the examination of the parachute design and the parachute test program. Parachutes are soft goods like airbags, and they don't model really well. You cannot go and run computer models of parachute inflations and performance. They just are not deterministic that way, so you have to test them. The problem with testing parachutes for Mars entries is you saw, this is a parachute that is meant to open at Mach 2 at 8 miles high on a planet where the surface pressure is 0.6% of the Earth's surface pressure. That's a test condition that can be done on Earth, and Viking did it, but is extremely expensive. And what it requires is that you really shoot parachutes in rockets outside the Earth's atmosphere and then slam them back into the Earth's atmosphere and do testing then. And most people think it would be about a $100 million program now. As a result, everybody that goes to Mars, us, Pathfinder, Mars Polar Lander, future landers on the drawing boards, all use the Viking test data. And they all design their parachutes to be what's called inside the Viking box. Okay? And there's a lot of arguments when you get outside the heritage, and we were, about, well, I'm inside the Viking box, but you're outside what's flown before, so how sure are you really that it's going to work okay? The part of this parachute that got us was the strength. Wasn't the ability of the parachute to open at high velocity, which we did not think was a problem, but it was the strength of the chute. Remember that the lander had gotten heavier, and so the chute had to get stronger. But the lander had volume problems, so there was no place to make a bigger parachute. So we had to trade off something. We had to go to thinner fabric or thinner tendons or smaller chute, which causes stability problems. So there was a big trade study being involved. And the question was, well, how strong is the chute going to be? Now, the way we initially tried to test this parachute strength was we dropped it in Idaho over at a drop range, and you drop it with a very heavy mass. And the reason you do that is when the parachute opens, it wants to stop in Earth's atmosphere, but you want it to keep going because you need to test its strength as if it was at Mars when the velocity is high. The difficulty is, with us, as we discovered, that the parachute takes so long to open, 1.5 seconds maybe, that the velocity builds up to the level where the parachute can't handle it anymore, and you get that. Okay. That was a bad day. And so we attempted to redesign the chute. We actually made it a little bit smaller, which worried us about stability problems, but turned out we ended up okay. But we really needed to do a test paradigm that would allow us to really test the parachute strength in a way that didn't have so many test fidelity issues like this did. And so what we did is, and some of you will recognize this, is we went next door. Okay, this is a picture at Ames in the wind tunnel. Okay, you can see the size of the chute. These are people standing underneath the parachute. And what we would do is we would turn up the wind tunnel a little, shoot the parachute out, and then crank up the wind to do the strength testing. And they saved our bacon by making that test available to us. We did have an early problem I didn't show a picture of, where the first chute, we tested it here, did not inflate. It's squidded, what's called squid. It just stays folded and kind of flaps in the breeze. And it turns out that that's caused because the vent hole at the top of the chute's too big. And so there's not, air just passes kind of right through the chute, and there's no pressure differential to force the chute to open. Fortunately, the first repair we tried worked. That was another big sigh of relief. Also, we discovered what I'll call the wind problem. Okay, the answer to whether or not you can land safely on Mars with airbags is what do you hit and how hard do you hit it? Okay, the what do you hit part is done with site selection, photography, some probabilistic luck, because in fact there's no place to land on Mars that's perfectly safe. Even in the Pathfinder photographs, there are places where if Pathfinder would have landed there, they would have failed. And that's certainly true for us as well. And then there's the question of how hard you hit it. How hard you hit it has two components. The vertical component that you can control by how high you cut the bridle, but there's a horizontal component as well. And that horizontal component is caused by two things. One thing is, as you would obviously see, is if the wind's blowing on Mars, it's going to carry the whole parachute and you sideways with it. The thing that's not quite so obvious is that, remember how the rad rockets fired on the back shell? Okay. Those are very large rockets. They bring this vehicle to a dead stop in less than 3 seconds. And if the back shell is tilted, it's going to drag them sideways. Okay. And so wind gusts coming down, wind shears coming down, cause the parachute and the back shell and the lander to kind of swing and sway. It's a pendulum with a very low frequency, but if the wind gusts are happening at just the right amplitude and just the right frequency, it can pump up the system. And so we included two things. One was the descent image motion estimation system. Don't you love the way engineers love acronyms? DIMES. Okay. Which is what Jamie, I think, was talking about in the video, where we took 3 photographs, 3 pictures, and we did image comparison between the 3 pictures for high contrast features to determine the velocity across the surface. That was a very, very reliable way of making that measurement, much to my shock. The other was we added the transverse rocket system. We actually measured how tilted the back shell was, and we kind of kick it. Now, this was not a gentle thing. We didn't just simply say, well, let's nudge it over. We had 2 states. We had a rocket facing sideways, and it was either fire or don't fire. So it's kind of like fixing your television set with a hammer, you know. Not working, bang, works. So a couple things happened. We added these things engineering-wise, but now wind became part of the site selection effort. Now, the problem with that is there's no wind measurements of Mars. Okay? There's no ground truth. We have at this point, we had flown through the Martian atmosphere 3 times, 3 different places, 3 different seasons. Statistics weren't good. We had a lot of surface measurements, but that wasn't helping us at altitude. And so what we used is we used basically the best scientists' brains they could bring to bear and Earth-like climatological wind models. And we built what were called mesoscale wind models. The project undertook wind modeling efforts. And to do these, we would set up a set of initial conditions over blocks of 500 kilometers by 500 kilometers on real Martian topography and run 10 days of climates and winds on 5 kilometer squares. And that took supercomputers here at Ames, took supercomputers at Caltech. We had a lot of people putting a lot of horsepower on that problem. We ran it a lot of times. 10 years ago, that problem is not solvable by the project. Okay? But because the technology was there, we had an estimate of what it would be. And in fact, we were able to go to Gusev, where Spirit went, because we were able to convince ourselves that the winds there were benign enough. And a very attractive wind site, a very attractive site in Valley Marineris called Melis, which was my favorite, primarily because the wall would be 5 kilometers high and would be a wonderful photograph. The winds there are 50 meters per second per the model, and that's just too dangerous for us to go to, so we couldn't go. We get to 2002, and we begin to put it together. The schedule had eroded a lot, and so in order to try and recover that, we did double shifting for what we call integration and test. The group of technicians and engineers that put the thing together, that get all the boxes and actually put it together and test it. Normally we plan that work on a 40-hour week, knowing that they'll actually work 60 or 70, and weekends are slack. We started out this project assuming that we would work prime shift and swing, that we would work 14-hour days, and this team, between the start of testing in March of 2002 and the launch of June of 2003, had one 2-day weekend. And it was Thanksgiving of 2002. They never for the rest of that time, they did not have 2 days off. But they saved our bacon. The actual testing exceeded our initial plan by over 1,000 hours. And we had high confidence by the time we launched that we understood what this thing was going to do. And fortunately, the environmental tests, thermal vacuum, temperature testing, vibration, acoustics tests, they were all successful. We did not have anything break during those. We shipped the spacecraft to Florida in January, February, March of 2003, 3 shipments. Remember, we had 2 spacecraft and a bunch of support equipment. And testing continued there, but we had 2 problems uncovered at the launch site. One required a rework to hardware inside the rover. The rover was folded up. Solar panels were folded up, and we had to get to the computer inside and replace a part. And we were able to do that, but that caused us a certain degree of consternation. And in the process of doing that, we fired the pyro devices, the things that, little explosive charges that deploy things and open things up. And when we did that, there was a fuse that connected, I don't want to get too esoteric here, there was a fuse between chassis and the power common, the negative side of the power bus, and that fuse opened as a result of that pyro firing. And so we didn't discover that for several weeks, and when we did, we kind of said, huh? And we did a bunch of testing. We finally understood what the problem was. We did some testing that indicated that it was not a design issue. We could survive that situation, but there was a worry that we had overstressed some parts. And that therefore, when we counted on the parts to work at Mars, they wouldn't work the next time. And so we had to go and dig up all the pyro devices that we had ever fired on the spacecraft and look at them to examine whether or not we had this overstressed condition. And of course, we fired a lot of them, and we didn't necessarily think that we were going to ever look at them again, so there was file cabinets and drawers at JPL. The search team was out, and only a few days before launch did we find the last 3, and we were able to give ourselves a clean bill of health. That was a close call. The spacecraft are closed out and prepared for launch. Some pictures. This is what I call the family portrait. This is Sojourner. This is, actually, it's Marie Curie, which is the flight spare of Sojourner. This is, I believe, Spirit and Opportunity. This one shows how the wheels fold up underneath, but the solar rays are out. You can just barely, it's not a good photograph for contrast. You can see the mast here. Here's what the wheels fully deployed. This was taken February 10th in 2003 at a media day at JPL, just before the first one was shipped to Florida. This shows the folded up rover. See how tight it is here? See these little cutouts in the side pedals? Those match the wheels, you'll notice. Okay, they're there so that you can close it up. These are the egress aids. They are meant to fall over the rocks and airbags to give the rover something to roll off of. You would think that the place to drive off would be down the pedal, but there's too much stuff here. And the wheelbase of the rover is too wide for the pedals, so it's actually best to drive off in between. You can see the solar rays are folded up here. This is the low gain antenna coming out here. This is the back shell in the background. We'll see it a little bit later. This is beginning to fold it up in Florida. Same kind of view for the rover. Now the pedals are beginning to fold these things on the outside of the airbags. Right here. This is a red tag item. That means you remove it before flight. We're very careful with those. Here's some boxes that aren't on the rover, you'll see. They're in the lander. They're for electronics to kind of open the pedals, things we need to land on the surface, but we don't need to roam around on the surface. And so we put those electronics in all those kinds of places. You can get a sense of scale for this thing from the people standing next to it. This is it all folded up. You know, they really aren't very pretty, are they? They're kind of ugly. You can see the thermal blanket here. Red tag items here. The gold foil is super. These are the pyro nuts that hold the thing together. This is it sitting up inside the back shell. This pink stuff is really protective coloring. This is not the size of the back shell. The back shell is really a gray phenolic kind of compound. And you can see it's gotten uglier. These thermal blankets, this is thermal blanketing material here to make the thermal design on the inside correct. Big challenge for interplanetary spacecraft is to keep it warm enough but not too hot, because it's a problem dissipating the heat as well as keeping it warm. You can see that the heat shield's on its way in to be bolted up right here at this interface. This is Spirit, all put together. This is the crew stage here. This is on a spin balance table. This thing actually turns. This is a several $100 million spacecraft that's going to sit on that thing and turn at 60 RPM. Kind of almost like frightening there. We spin balance the spacecraft because it spins on its way to Mars for attitude stabilization and control. And the launch vehicle spins it during the launch. So it needs to be balanced so that the moments of inertia and center of gravity are all correct. And so we spin it, and then there's little doors around that we can put masses inside to correct the products of inertia and the cross products of inertia. This is sitting on the third stage of the Delta launch vehicle. We launched on a Delta II launch vehicle. It's a 3-stage launch vehicle. This is actually the third stage. The way that Delta does their launch vehicle processing in Florida is they bring the third stage to you in your facility. The payload handling facility for MER was about 11 miles from the launch pad. And so they actually bring the third stage. This is actually, you can't see it here, but this is actually a truck. It's on wheels. This is the third stage right here. Here's the separation plane between the spacecraft and the launch vehicle. This is the spacecraft we've just seen. These are remove before flight items. This was a test, right? The red things are removed before flight. These are covers over the solar arrays, so you won't damage the solar arrays in handling. And then they put a big can over this, and then at 2 o'clock in the morning, so you don't have traffic problems, they take a couple, 3 hours and drive over to the launch pad, and then they pick it up on a crane and put it on top of the launch vehicle. And when they do that, it looks like this. This is Spirit sitting inside the fairing. We'll take a look at this view. This is remember this is a 3-stage launch vehicle. This is the top of the first stage of the Delta. Probably you're 90 feet off the ground at this point. This white thing here with the skirt at the top and the bottom is the second stage. Here's the third stage we just saw. There's the separation plane, there's Spirit, and here's the fairing. And this is looking in the other view. You can see the clearances here. Very tight. Just enough so that the vibration doesn't cause the two pieces to hit together. On other fronts, as the hardware was getting together, the airbag fixes were fully successful, drop tests were successful, and the parachute issues were resolved. We had simulations that tied together entry, descent, and landing design. We actually, I'll tell you about in a second, the airbag and parachute capabilities and the wind modeling. The way we validated entry, descent, and landing was we basically simulated the entire profile that you just saw in a computer running flight software. And we would buffet it with an exterior environment that we would simulate. So what we would do is we would go to the wind model people and we would say, give us a wind profile. And they would give us one. And we would throw that into the simulation and we would run entry, descent, and landing through that simulation. So we would get all the pressure differences, the wind differences, all the real atmosphere or all the modeled atmosphere differences. And then we had a terrain model for the ground. And so when we got to the end, we would cut the bridle and we would bounce this thing on a terrain with a set of rocks and craters and everything. And at the end, we would say, well, let's measure a couple things. Did we cut the bridle above the ground? That's always good, right? Okay. Yes, no. Okay. Did the airbag survive the hit? Yes, no. and we would run 2,000 case Monte Carlos. And early on in this process, we had trouble with the simulations. Later on in the process, we had to tweak some of the design parameters. There are hundreds of design parameters in that sequence that you saw that you can play games with in order to change the timing relative to things another. Okay, and we eventually got to the point where we felt that the probability of a successful landing at the two sites was probably somewhere between 90 and 95%. Okay, now don't take that, I mean, this is a one significant figure, right? Because this is, you're dealing here with models of reality when you don't understand the reality. But this again is another area. Pathfinder did simulations the same way, but they had much less technology to work with than we did, which means that they didn't have the wind models, nor could they have coped. They did not have terrain models like we had, nor could they have coped. So although their methodology was the same, we had a much higher fidelity and I think probably more credible answer than they did. Based on those results, the project recommended going to Meridiani and Gusev. And Dr. Weiler, the associate administrator that has the final approval, agreed with us. So this is a topographical map of Mars. This is false color. It is topological. Blue is low. White is very high. We have to land, there's what's called the MOLA reference geoid, or aeroid, which is, MOLA is an instrument, a laser altimeter on Mars Global Surveyor. That basically establishes sea level on Mars. We had to land lower than 1.7 kilometers below sea level in order to land successfully because we needed that much atmosphere to slow down. One of the challenges I have on the Mars Science Laboratory project for 09 is I'm supposed to be able to land at 2.5 kilometers above sea level. So I have to find additional ways to slow down. And one way to do that is to not fall through the atmosphere but to offset a CG and use the lifting body characteristics of it as well. Blue is good. As you can tell, green is about where we were stuck. So Meridiani was right at our limit, and Gusev crater was over here. This is where Beagle was supposed to land and may have. Pathfinder landed here. This is the Viking landing site 1. This is Viking landing site 2. Meridiani was very favored because it had hematite there. I don't know if you've read about that, but hematite is a mineral that on Earth almost always, but not quite always, forms in the presence of water. And since the goal was to chase the water in the geology, this was a very, very preferred place to go. Gusev, I don't have a good picture of it here, is a large crater, 120 kilometers across, with hundreds of kilometers, what clearly looks like a river flowing into the south end of it. And clearly looks like it's a ponding region where water should have collected and sediment should have fallen. So this was a mineralogical site. Go to a place where the mineral says water was there. This was a topographic or morphological site. Go to a place where it looks like water had ponded. On other fronts, software could not be done on time. Have you heard this before? And so we committed to a post-launch software development effort for the surface mission. We could launch it, we could get to Mars, we could land on Mars, but driving the rover was going to be chancy, so we took the next 7 months to do that. June 10th, after some delays, closing out the pyro problem, and 3 days of bad weather, we launched Spirit. And on July 7th, after some launch vehicle issues that had to be resolved, we launched Opportunity. I didn't see either one of these, by the way. Blockhouse, Pasadena. So I've never seen a JPL launch. After we launched, the spacecraft behaved beautifully. The navigation was perfect. No sign of the meters versus feet problem, right? Metric versus English units. But life is not simple. Further software testing uncovered 2 bugs that required fixes in entry, descent, and landing. One that was discovered less than 2 weeks before, which required sending a real-time command the afternoon of entry, descent, and landing. So I was about noon on Saturday the 3rd of January describing to the director of the laboratory and Dr. Weiler why it was necessary, after 300 entry, descent, and landing test runs that had worked just perfectly, that the fact that I had 3 that didn't caused me to want to send a real-time command that afternoon. Okay. That was a very interesting discussion. And I'm not sure that it wouldn't have been fine. You know, it's the classical problem you get into these kinds of things. You have two events, both of which you believe are low probability, but one you think is more probable, even though low, than the other one. And a lot's riding on this. I mean, there's a lot riding on this. The Mossbauer spectrometers both had anomalies on the way to Mars after launch that could not be explained. And we tried. And we did tests. But when you land, they fix themselves. The theory is that they don't like vacuum and they don't like zero gravity, and that they really liked a little bit of atmosphere and that they really liked a little bit of gravity. But we could never understand why. From an engineering standpoint, that should be true. But the fact that they both repaired themselves, I think, is some strong evidence that that's likely what was going on. You may remember that in November of last year there was a tremendous solar flare, way off the scale of previous experience, that caused us some operational difficulties. It caused some issues with the Odyssey orbiter that by then was at Mars. We had the same memory that they did, and although we didn't see any anomalies, it caused us to do a cold boot of our computer in flight both times, both spacecraft, to reset the memory registers, configuration registers. And it also meant that when the part of the sun that it was active was facing the spacecraft, there were certain operations that we would not do. So I took my operational team that was already working very hard and said, well, 50% of the time you can't do certain things. So you got to crowd all that into the other 50% of the time and work harder. So that was a struggle. You'll also may remember that there was a dust storm on Mars in December. And dust storms at Mars, what they do is they elevate dust in the atmosphere. That dust, sunlight hits that dust, and that layer of the atmosphere gets warm. And so it basically inflates the atmosphere, and it changes the pressure profile. And so for us, the question was, are we opening up the parachute in the right place? Do we have enough time to get to the surface so that all these steps accomplish and we can get the bridle cut on time or not? So for Spirit, we actually opened the parachute up a little high, and it turned out that when we reconstructed the Spirit data, it opened up lower than we expected, even though we opened it early. And so on opportunity, we moved it up again. And some people think that if Beagle was not able to accommodate that, that may be one of the possibilities on their failure list. We did 6 the software development for the surface was completed, and we did 6 operational readiness tests. None of them worked well. Okay? The actual mission has gone a lot better than any of the testing we ever did. Okay? But, finally, can I have the next video, Mike?
Flight now.
Go now.
The Doppler signature indicates three-stage separation has occurred.
Copy that. All systems are go for entry, descent, and landing. We are roughly 11 minutes, 48 seconds from landing at the Gusev crater in the southern hemisphere of Mars. At this time, we'd like to invite you to sit back and enjoy the landing. Atmospheric entry, 5, 4, 3, 2, 1, mark. The vehicle has now hit the top of the Martian atmosphere. The velocity will continue to increase for the next minute. We are now moving at a speed of 12,192 miles per hour. Downrange distance to the landing site is 437 miles.
The unconcerned project manager.
Expected parachute deploy in 5 seconds. 4, 3, 2, 1, mark. Current altitude should be approximately 25,000 feet. We are awaiting confirmation the parachute has deployed. We see a parachute. Parachute was detected. Current altitude 8,000 feet. Moving at a speed of 173 miles per hour, we are near our terminal velocity. Lander separation event has been detected. The radar is in lock and we have a good solution on the ground. Expected retro rocket ignition on my mark. Mark. Getting confirmation from the spacecraft that retro rocket ignition has occurred. At this point in time, we should be on the ground. Now 6 minutes, 37 seconds from atmospheric entry. Still awaiting signal that we are on the ground.
No signal at the moment. Deep Space Network tracking stations in Canberra and Goldstone are still searching for the primary signal. Stand by. What do we see? Electronic tone sent from the rover indicates that the rover has landed base pedal down, which means right side up.
Remember that lady right there, that young girl.
And a good evening from the flight deck of the Opportunity. At this time, we are approximately 5 minutes, 53 seconds from landing at the meridian planes near the equator of Mars. Over the next minute, we should begin to receive electronic tones from the spacecraft indicating the gradual deceleration. This time, parachutes should have deployed. We are waiting confirmation that has occurred. Current altitude, 25,000 feet.
Parachute deploy has been detected.
Now, positive indication of parachute deploy.
Semaphore has been detected.
Currently at an altitude of 18,000 feet. At this time, the radar should be active. We expect the radar should lock on the ground in approximately 15 seconds from now. Current altitude 11,000 feet. Current velocity 180 miles per hour. Currently decelerating at 0.4 Gs. We expect that the airbags will inflate approximately 20 seconds from now. Current altitude 4,000 feet.
Radar solution matrix 21.
3,000 feet. The radar has a positive lock on the ground. We have a retro rocket firing solution. Retro rocket ignition on my mark. At this time, the retro rocket
has fired.
We have confirmation the retro rocket have ignited. At this time, we are 5 minutes, 55 seconds after entry. We should be bouncing on the ground. As the spacecraft is bouncing on the surface of Mars and rolling around, the antenna is pointed in many different orientations.
We're seeing it on the LTP. Very strong on LTP. We're on Mars, everybody.
This is the sweetest spot I've ever seen.
I want you to, I'll talk at the very end, but I want you to remember there and capture the lady, the young girl I pointed out to you, and I'll mention her at the end, and also the American flag that was sitting in the back of the second one. Okay, that was sitting in the mission support area, and I'll talk about that at the end as well. So, this was the Spirit landing site. This is the size of the landing ellipse. You can see there are places here which are not good. Okay? But from a probabilistic standpoint, there's a very high probability of success here. And because of the atmospheric issues I pointed out to you, we landed a little bit long. We should have landed here, we landed here. Steve really liked this. Steve Squires, the principal investigator, because these are dust devil tracks. And he thought they would clear off the dust and you would get a better view of the rocks underneath at that point. This is a closer view of that. The rover lander hit about here, rolled to here, went up to Bonneville Crater. I'll show you a picture in a second. And then down, and we're actually down here now. This has been about a 3-kilometer drive from here to here. The objective of landing at Gusev was to look for sedimentary material, but everything they've seen has been basically basaltic in nature. It's clearly, whatever's been there has been overlain by some either volcanic activity or ash activity or whatever. There was some hope that a crater would excavate sedimentary material from below, but that did not happen when they went to Bonneville. It was not, they didn't see anything there. They are seeing outcrops up here and stronger evidence of water presence up here. They've seen bedrock up here. And so, and there may be some better science discoveries up here. Right now, it's getting to be winter at the landing site. As you recall, these things were supposed to last for 90 days, and we are well past double that now. But it is cold because it's winter, and the sun on the solar panels is at a high angle, and there's dust on the solar panels now. So the daily insolation for Spirit, which was about a kilowatt hours per day, 1,000 watt hours per day, is down in the neighborhood of 350 to 300. It also has got a bung wheel. It's got a wheel that is taking high current to turn now, and so they're dragging it about 90% of the time. So they'll probably go into kind of a hibernation mode for a while. The sun will start coming back in October, and things should pick up, and the rover should get warmer. There is a chance that these rovers could last a very long time, meaning many more months, or they could die tomorrow. It's going plus and minus, it's a 100 degrees centigrade swing a day on some of these components. This is the empty lander. Always a beautiful picture. Adirondack. Remember the Spirit anomaly? I don't know if you remember that, but we had the computer go into an endless reset loop because the flash memory file system had a bug in it. We used flash memory for storing products, and we had the file management system that was in RAM could not cope with the large number of products that we were doing. And so when at one point in time it requested more system resource from the operating system, the operating system said no, and it did not have a graceful way to get out from under that, and so it reset. And when we didn't hear from it for a day, and we got kind of concerned, but after a couple of days of very good troubleshooting, some very, very smart people, and the fact that some of our software people had actually put some backdoors into the code so that we could get around the problem. Can't trust those software people, can you? This is Bonneville, which is where they were hoping to see some sedimentary excavation. And you can see it's very much the same dust-filled as they had seen before on the plains. The East Hills, and a better view of that, where they are right now is they're up just on this coal right here. And they're looking up the hill. This is bedrock, which is always nice to get to, and they're kind of going around this way. They're trying to always keep on the northern side so they can keep good sunlight on the solar panels. So they're very careful what the slopes are. You only park in north-facing slopes. You only do this, you only do that. And so it's slow going right now, but things are still going okay. Opportunity. This is a picture from orbit. This is from the Mars Mars orbital camera that's on Mars Global Surveyor. This is actually the lander inside this crater. That white dot is real. Okay. This little area here, which looks different than the rest of the terrain, we think is where it bounced first, and the effect of the rocket firing. You'll notice the probability that we would hit here and roll there is low. There happens to be a rock outside here called bounce rock that it's the only rock for, as far as you can see, that's on this plane. We actually bounced on it, and it bounced us in the crater. So we were very lucky. This is where the heat shield hit, and this is where the parachute is. Now, they spent about 60 days roaming around inside this crater, small crater, where the bedrock was that you saw in the video. And then they went over here, roamed around the south side of this. I'll show you a couple pictures. And now they're inside this crater. They've crawled inside the crater, trying to follow the layered sedimentary deposits down. This is the bedrock that they saw. You can see the layering here that led them, after many weeks of investigation, to conclude that this was in fact sedimentary deposits laid down in a salty sea. Now, this is a very salty sea, and it is very high, very low pH. It's a very acidic sea. And in fact, some people question whether or not it's so acidic that life would have had no chance to form here. But a lot of investigations are now ongoing to answer that question. This is a picture of the lander. And looking back at the crater, you can see, this is after they rolled out, you can kind of get the history of what they did. Okay, all the tracks around the crater. The park rangers will be by in a second with our fines. Take only photographs, leave only wheel prints. Is that the... Okay. You see these things here? Right there? Those are airbag bounces. You can see where it compressed the dirt. This is the other crater. You can see this outcrop here, but much more interesting is this outcrop here, which clearly looks layered, is probably 5 to 8 meters high, much too steep to get to either from above or below, but they tracked it around the crater and to a place where they could get to. And that's what they've done, is they've crawled in. This is looking back toward the rim. You're in the crater looking up. And these are little rad holes where the rock abrasion tool has drilled into the rocks, and you can see this layered structure here, many meters thick, leading them to conclude that the age of this sea is much longer than they had thought before. Now, you see what looks like clear differences in these layers. Okay? But as far as they can determine, that's textural only. The chemistry is very, very similar. There's not a lot of chemistry difference between the groupings. Why did Mir succeed? Well, the caliber of the people and their commitment. There was probably 4,000 or 5,000 people around the country that devoted their lives to this project for 4 years. I've often told the story. We were having trouble getting motor and motor gears built, and I went to a little place out in Boulder, Colorado that had signed up to help us out. And it's like in an industrial park, like every industrial park you've seen. I mean, it was out in the middle of nowhere. I drove into this cul-de-sac. There were 4 brick buildings. This was one of them. They had 70 employees. I sit out in front of this thing, and I said to myself, if they don't work, we will all fail. And they really came through for us. And there's, I have 1,000 stories of people that did that for us. I was in Florida for the second launch, and this very elderly, frail lady was in the front row. And she was from ILC Dover, and she was one of the seamstresses that had stitched the airbags. Okay, and she had come to the launch to watch the launch, and just a degree of commitment. And you saw the video and how young those people were and how diverse those people were. The young lady I pointed out, she got to work on this project. It was her first job out of school. Okay, and people said, well, what did she do first job out of school? It turned out that in the middle of cruise, we had some problem, an issue with the battery conditioning for the landing, and she was in charge of developing the sequence to do that operationally and to test it, make sure it got tested in the test bed, and to sit in the MSA and make sure that it clocked out okay. So she had a level of responsibility at a very tender age. We had an incredible amount of support from JPL and NASA management. I mean, I got money when I needed it in the same fiscal year in which I asked for it, which is unheard of. You all know, don't you? Yeah. And I, if I needed personnel or I needed facilities, there was no questions asked. So this was a very high priority job, and everybody knew it, and that made my life very simple. I made a lot of enemies, which is why I'm visiting you today. I'm out of town. And then I alluded to the technology. Clearly there were places where the simulations and testing were helped by the computer technology. Clearly in operations, a major step forward. Everyone's now in a workstation environment. There are no really integrated large platforms anymore. In addition, the project itself with its daily technology had made major steps forward. Very quickly in the project, everybody used a laptop. I don't think anyone had a desktop computer anymore. The lab is wireless. We had electronic file. We happened to use a Xerox product for document storage. Had all conference rooms were wired for projection. The Columbia shuttle investigation people came out and were kind of surprised at the degree of which the electronic access. And I claim it probably got us 20 or 30% in productivity because of the ability to have very effective meetings, be able to get to product, have everybody on board. If you want to sit through a meeting and read your email because you're bored, you can get that done too. One of the things. Couple comments on what's important. People ask me, why do you do this? Why do we do this? Clearly, the science is science and it's good for us, and the exploration is exploration and it's good for us. But we do this also to inspire. We do this to to get the young people of the country interested in science and technology, and to understand that they can do this too. Jennifer Trosper, the lady in the maroon jacket who was the mission manager, she was my project engineer and she was the mission manager for Spirit. She comes from a farm in Ohio on her way to MIT. And she sat at one press conference and she said, she was talking to the press and she said, I was thinking of my to-do list in high school, which was, feed the goats, paint the barn. And my to-do list today was talk to the president, drive Rover on Mars. She said, things have gotten a lot better. I received this email on the 28th of January. Mr. Theisinger, my son Matthew, who recently turned 7, presented me with his version of the NASA JPL Mars rover when I came home from work earlier this evening. Built from Legos in his imagination, I thought you would enjoy seeing his handiwork. On behalf of Matthew and our entire family, our congratulations on the accomplishments of NASA and the JPL. We are awed by spirit and opportunity and sit in wonder in front of our TV and our PC screen every day as we watch the events on Mars unfold. We are proud to be Americans, citizens of the country that has taken the lead on the exploration of space for the past 50 years. Your work inspires us all. Perhaps Matthew will someday become an engineer or an astronaut and will recall sitting at his Lego table and building his own rovers and space vehicles. Whatever Matthew becomes, you have made his life more interesting and stimulated his mind and imagination. And then a final note, the flag on the back of the MSA. Okay. One of the people who worked on the project, son, graduated in graduated in that summer from the U.S. Military Academy at West Point, and was married in August and went to Iraq in September. And that flag is from his casket. So, a measure of what's really important in this world, you all need to take home. Thank you very much.
For those of you that are going to ask questions, please hold it away from the end, because otherwise you're covering the antenna. And please hold it close to your mouth and start with your name.
Michael Coulter. I was wondering if there were any concerns about contaminating Mars with Earth microbes and...
Yeah, there is a international set of treaties on what is called planetary protection, and it restricts and controls how clean the spacecraft that you take to Mars has to be. There are basically, for landers, there's another set of rules for orbiters, and their probability of crashing and things like that. But for landers, there's two sets of rules. There's a set of rules if you are not a life-measuring mission, and we were not, and there's a set of rules where you are a life-measuring mission. And basically it restricts to some number the microbe count that you can take, the spore count that you can take to Mars. And so what happens is equipment goes through dry heat, what is called dry heat microbial reduction. At the box level, we put things in elevated temperature, if they can be done that from a design standpoint. We do cleaning of the exterior surfaces. You saw the suits that the guys were wearing. That is not only for, equipment cleanliness and contamination of optics, it's also for that reason. And we keep basically an error budget, just like we keep error budgets for other things. It says, okay, we can do that. The project has to provide a planetary protection plan to the planetary protection officer at NASA, and that person has to approve the launch, and he answers to only the administrator. So there is a quite crisp set of rules in place. Now, I think that the rules are in the process of being updating for a couple of reasons. One is biology and our understanding of how the survival of organisms has gone leap years from Viking, which is where the roots of these rules all are. The second thing is that The Odyssey spacecraft has a gamma ray spectrometer on it, and it has found a lot of buried water, which people think is ice below the surface. So people are now concerned that, in fact, although the surface is felt to be sterile because of ultraviolet radiation and the heavy acidic nature and oxidizing nature of the chemistry, it's possible that below the surface could be quite hospitable. So I think they're re-examining the rules based on that, which will make the life of the engineers more difficult, but that's what we get paid for.
Dan Henderson, would you please tell us the backstory of the English metric conversion problem?
Well, navigators measure in metric units, and propulsion people measure in pounds force, and you can't get the guys to change their minds. And the problem is that there was really no end-to-end validation of the process to close out the discrepancies that we're seeing. The Mars Climate Orbiter spacecraft was what kills the navigators is non-gravitational forces. Okay, anything that is non-gravitational, they have to accommodate. They look at solar pressure, they look at everything. And if you've got thrusters firing on the spacecraft, if you don't have them in couples, where you fire this way and this way, if you only have them unsymmetric, every time you fire a thruster, it adds a little bit of force to the spacecraft. And they've got to model that, and it drives them crazy. MER was a spinner, which meant we almost never fired thrusters. They loved us. Okay, that's why the navigation on this spacecraft was so good. But Mars Climate Orbiter was not a spinner. And it used reaction wheels, and the reaction wheels had to be offloaded by firing thrusters periodically. And rather than doing it once a week, like everybody expected would happen during the design phase, they ended up doing it twice a day. And so the navigators were getting a lot of non-gravitational forces, and it was causing the solution to hunt. Okay? And no one asked the question, could something else be going on here? Okay? They thought they knew. Okay? And by the time they got to the planet, and they got, the issue with when you're at the planet is you only feel the gravitational field of Mars maybe 18 hours out. We were prepared to do a maneuver 6 hours out if we felt that the navigation had us in the wrong place. Okay? But they were not. And when they found out late that they were falling deep in the well, they had no place to go hide.
Hi, Brendan Wilson. There was a lot of talk about the things that were done to make sure that the lander landed properly, but I wonder if you could talk about what was done to make sure that what was left behind when the bridle was cut didn't collide after
the recontact problem.
Yeah, so that it didn't,
that was only addressed probabilistically, in the sense that the rad rockets were still firing with a very high thrust for about a second and a half, uncontrolled, unstable. And so the assessment was made, as it was made on Pathfinder, that the heat shield would drag the parachute away. Now, one of the things that both the photography at Gusev and the photography at Meridiani have shown is several things. A, for all that beautiful video, the landers did not hit very hard. They hit about 10 Gs, they rolled about 300, 400 meters. Okay? The heat shield and the parachute came down pretty close. If you looked at those photographs, they were not that far away. So I think that people will relook at that problem if we ever do it again. Okay, now I've got the same thing on my mission. I've got a stage that that's going to depart from the lander I leave behind. Okay, and we are wrestling with the problem of whether we're going to try and do that in an uncontrolled or a controlled way, or what we're going to trust here. Okay, but the solution at that time was it was done probabilistically. The other recontact problem was a heat shield. Okay, we in fact added about 30 kilos to the heat shield to make sure its ballistic coefficient was much higher than the parachute, and it would fall away from the lander.
Hi, I'm Warwick. Wanted to ask two questions. One is, was that a standard Delta launch vehicle there?
Yes. Okay. Well, the first one was a Delta II, and the second was a Delta II Heavy.
And second question, you went to a lot of trouble to fire the retro rockets long above the surface and then fall the rest of the distance and hit the ground pretty hard. I was wondering, why you had to go so much higher, cut so much above the ground.
If you look at the dispersion analysis for the radar signal and the solution and updraft and downdrafts, you cut that high from an average sense to make sure that your 3 sigma low case isn't below the ground. Okay? And in fact, in both cases, if the reconstruction indicates that we cut low. One case we cut at like 8 meters, and the other case we cut 10. Now, 8 meters sounds like a lot, okay? But you got to think that 8 meters is the center, okay? An 8 meter cut means the airbag's about 1.5 meters off the ground. Yes?
Mike Smithwick, and considering that the original planned lifetime of the rovers was for 90 days, an operational lifetime, and now we've just reached to understand 200 souls for Spirit. Is there an open-ended commitment to funding and personnel for the rovers as long as they last, or are they going to say at the end of a year, for instance, shut them down like the Viking?
I'm not in charge of funding. You can turn the video camera off now. NASA has a problem, or the Mars program has got themselves into a box because Mars Global Surveyor, which was supposed to last 2 years mapping, 3 years relay, is now on year 7. Odyssey shows no signs of abating. We show no signs of abating. The history of JPL spacecraft is that they generally either don't work or they work a long time. And the funding profile really hasn't taken that into account. You know, the mindset of extended missions is that you're going to get the bulk of your science at the beginning, and then the science will kind of trail off. Viking lasted 5 years, okay, but you don't hear very much about the end because it was really just a meteorological station at the end. They'd done all the photography, they'd done everything they could with the arm. The beautiful thing about mobility is if you don't like where you are, you move. Okay, and so it's a new landing every day. If you look at it, we got into Endurance Crater at about day 90. Now, it takes a brave man to look at that and say, well, 90 days, funding's over, goodbye. Okay, so I think that they will continue to fund it. Now, that doesn't necessarily mean that they'll fund it at the same level. The science teams, which were at JPL, and we were all operating on Mars time, are going home. They're going to operate and plan remotely. Mars time has changed to Earth time. We do much less on the weekends than we do before. We have dead days and not so dead days. So the whole level of activity has gone down. People like me in my new job are busy stealing good talent from the project as quickly as we can. Okay? And so there are pressures that will reduce the funding requirements, but it doesn't go to zero. And I think that, you know, you've seen the uproar with Hubble and things like that. It's difficult to believe that they would actually turn them off. But they will certainly, you know, try and lower expectations and get the workload lower so that the funding goes down as well.
Hi, Josh Pincus. 2 quick questions. One, what role, if any, did Sun play with the technological successes you talked about? And sorry, it's the corporate question, but it's a good one.
You were essential. Didn't I mention that earlier?
And the second is projecting out a few years. Can you give us a quick sense of what projects we can expect to see in the next couple of years?
The Sun and its technology was involved clearly in the ground system, and I'm really the wrong guy to ask about that because there were a lot of technological advances there. I, like all project managers, don't know anything about the projects I manage. In the future, there's an 05 orbiter that will launch in 05 with a very good camera and a very good set of spectrometers. In 09 is the next rover, which is capable of being nuclear powered. That decision hasn't been made yet, but presumptively will be. It's going to last substantially longer than the MERS design lifetime, have greater mobility capability, and carry significantly more science. MERS science payload was really 5 kilograms. And the new rovers will carry something like 65 kilograms, including analytical instruments that will actually take cores and samples and digest them and do more chemistry. In 11, there's something called a test bed or exploration vehicle. That's part of the initiative for exploration, and that's not well defined yet. 13 should be another sample to return opportunity. That's where people think sample return may land now, is in 2013. There's also a biological lander that people are talking about. There's several forks in the road that can happen after we get 2009. And the plans for the Mars program basically fund a mission or more every opportunity, which means basically every 2 years, out past through the next decade. So there's a lot of both orbital and surface activity being contemplated.
Doug Doyle, sort of a follow-on to what's coming. How do you balance reusing systems and techniques that have already been proven versus cool new things that are really tempting to do?
I'm a project manager. Cool new things are never tempting to do. A facetious answer, but like all humor, has an element of truth to it. The Mars program has a substantial technology arm, and are developing feed-forward requirements. There was a set of feed-forward requirements on the Mars Exploration Rover Project. We actually exchanged data with Mars Express to prove out the international network capabilities of the Mars Express receiver with us. We operated both rovers simultaneously. That was actually a requirement that we do that to show that we could do that from a ground standpoint. There were several advances attempted to be made in the ground system to try and get the cycle time down and things like that. The challenge is the projects are going to use what they can get that satisfies their needs and is make play. The challenge is to have the new wonderful things be ready to go at the time when the projects are ready to pull the trigger in terms of technology readiness. For my project, my PDR is in 2006. Okay, guys have got to be ready in 2006. I got some long lead flight hardware items where if they're not ready now, it's almost too late. But there's some software and planning and other ground technology items where we're a year, 18 months from having to make hard decisions. So that window is open. I think a combination of technology funding from the base program, getting plugged into the project so you're filling a need, okay, and then being ready is required. I've been in operations over several projects, and the problem we all get into is we are optimists. We feel that we can do more than we can. It will be done faster than it will. It will be done cheaper. There is nothing more unforgiving than a planetary launch schedule. Okay? If you don't go to Mars in a 20-day period in May and June of 2003, you don't go for 2 years. There is no forgiveness on that schedule. And if you're not ready to land on the 3rd of January, you're out the door. So that colors a lot of decisions.
Yes, Brian Berg. Had a couple of questions about the dust issues.
Sure.
If you could address that, for example, dust buildup on top of the solar panels and that affecting the lifetime of on the planet, as well as affecting the mechanisms of the rovers.
Well, you were supposed to ask me why we didn't think of windshield wipers, because I always get that question. The dust falls all the time, and it falls at about 0.3% per day or something like that. By now, we should have had about 20 or 25% of dust deposition decrease due to dust deposition, and that's about what we've been running. The dust is very fine, extremely fine, and the adhesion of the dust to the solar rays is probably much tighter than the dust on your table at home, and probably also partially electrostatic in origin. Remember, there's no humidity. I mean, electrostatic buildup is probably quite a mechanism at Mars. The analogy I always draw is, you get dust on the front of your television set, right? And it's a vertical panel in a 1G field, so you shouldn't be surprised if you can't get it off a solar panel. We did not think too much about wipers or plastic things that we would rip off, or turning the solar arrays over, having panels on the other side. Because we felt, A, we had signed up for 90 days, and as long as we had 90 days, there was no reason to make it more complex and more risky. And secondly, everything you do has its own failure mode. And one guy asked me, he says, well, you've got motors on the panels, right? Yes, you do. So you could fold them up and, kind of shake them. And I told him I would not do that.
Hi, Steve Kastner. You said a couple of times that the bounce was from a lower height than what
We expected.
you expected. In the videos, were those recreations from the real recorded data of what happened, or
Yes.
are those just approximations?
No, those were, we had recorded IMU, inertial measurement unit data, from both the base body and the back shell. And we reconstructed the profile down and the bounces. The bounces were very gentle. We bounced at less than 10 Gs. Adams 40 Gs didn't happen. And we only rolled, like I said, shorter, and that may have been because we think we rolled a little bit uphill. If you cut from 10 meters and you roll up a 10-meter hill, you've lost all your energy, right? I think there was probably downdrafts in the atmospheres caused issues on both landings. That was, particularly down low. The radar makes its final estimation, and at some point it's simply got to say, okay, I'm going to fire the rockets now. And the rockets actually fire quite high. You're probably 100 feet up when the rockets start to fire, because it keeps going and then slows to a stop. And so that all part of it is non-modeled, non-modelable. That's just dead reckoning. You get what you get. So I think that's what was in it. But the actual reconstruction was done from hard telemetry.
Let's take one more.
Okay. Who's the lucky winner?
I'm Steve Williams, and I was just curious if you're able to work out why the one wheel failed.
We think it's lubrication. We have tried to heat it and operate it in a way to kind of try and move lubricant around. These are lubricated gearbox assemblies, and we think that that's it. As far as I know, the guys have looked at the test data and the inspection reports, and there's nothing unique about this one. So this may be a Maverick. And if it is, this may be getting to the end of the useful life. We tested these things for 270 days. We tested the mechanisms. Our margin philosophy at JPL is we test mechanisms for 3 times their nominal life. And so almost certainly for these wheels and things, we are getting to the point where we're right at the edge of which we demonstrated margin. So we could be close to a cliff or we could not be close to a cliff. This may just be the first of a Gaussian distribution of failures that we'll begin to see now. I personally believe that what will happen is it will not just quit. I think it will, like me, grow old, and walk a little slower and get a sick wheel, and suddenly the camera won't work quite right, and those kinds of things. And eventually it may become so painful to operate that financially it's no longer worth it because of the level of difficulty to get it to do anything. That may be more than just let's turn it off. It just may get too sick. Thank you all very much.
Pete, what a microphone? Oh, yes, we'll say it. Had the microphone on? Thanks. What a great story. And Pete, I want to say, on behalf of everybody, thank you very much. And not only did those heroes that we saw in the pictures, but I think you're a tremendous hero, too, for the engineering community. Thanks so much. And a small token of our appreciation of the Computer History Museum for this evening.
Thank you very much.
And in addition, Glenn, I have a special one for you as well, if you'd accept that on behalf of Sun. And again, thank you, Sun, so much for sponsoring tonight.